electrical fundamentals. We'll look at the principles of operation and some specific construction features of the AC generator. There are many different types of power plants: hydroelectric, coal-fired, oil-fired, gas, and nuclear power plants, all used to supply efficient electric power. These power plants all share the same purpose, converting mechanical energy from whatever source into electrical energy. It is the generator which converts this mechanical energy to electrical power. The generator is the heart of any power plant. Well, let's look at a simple generator. Each time the field of a magnet moves through a coil, voltage is produced. Mechanical energy, motion, plus magnetic flux create electrical energy. The efficiency of this can be increased in several ways. First, by making both poles of the magnet work at the same time. A second coil placed opposite the first will produce voltage. By winding this second coil in the opposite direction from the first, both coils will produce identical voltage even though they're affected by opposite poles of the rotating magnet. Instead of two circuits with identical voltages, we'll tie the second coil in series with the first. Now, instead of two separate circuits of equal voltage, there's just one circuit with twice the original voltage. Obviously, the further the magnet's face from the coil, the less effective it becomes, and less voltage produced in the coil. Even when the magnetic field is close to the inner edge of this coil, a large part of the coil wire is quite some distance from the strong area of magnetism. The wire on the inside of the ring is creating most of the voltage here. Now let's make a practical generator. The donut-shaped outer ring, which is called the stator, will be replaced with a long iron cylinder. By putting two slots inside surface of the cylinder, directly opposite one another, the coil could be straightened out and inserted into one slot and back through the other. Now there's a single circuit lying close to the inner edge of the stator. Efficiency can be increased further by passing this wire through both slots a second time. Since each slot holds two sections of the single coil, voltage will be doubled. By placing a maximum length of conductor as close as possible to the inner surface of the stator, increased generating efficiency results. Next, that bar magnet will be replaced with a balanced steel rotor which fits closely within the cylindrical stator. This rotor will be permanently magnetized. When the magnet and relative motion. Look at the voltage generated during one full revolution of the rotor by watching this meter. In the first half rotation, the voltage increases from 0 to peak when the rotor fields were closest to the coil, and then it goes back to 0 as the fields pass. As the opposite poles of the magnet rotate past the coil, voltage develops in the other direction and then returns to 0. This completes one full cycle. By measuring the number of cycles produced by the generator in 1 second, we have a measurement known as frequency. Recently, an international term for cycle, the word hertz, was adopted, and both mean the same thing. The abbreviation for cycle is usually the sine wave symbol. Hertz is shown as Hz. The two-slot or two-coil generator with its two-pole rotor generates one complete cycle for each full turn of the rotor. For 60 cycles, it will rotate 3,600 revolutions each minute. Instead of just two magnetic poles, let's give the rotor 4 poles. Now, each full revolution of the rotor will create 2 electrical cycles. Each full revolution will create 2 electrical cycles. If 4 slots were evenly spaced in the stator cylinder, we can space the coil circuit to take advantage of all 4 stator poles at one time. And now a 4-pole generator is created, and one full revolution will produce 4 changes in polarity in the single coil circuit. The 4-pole rotor produces 2 full cycles within the coil circuit for each full revolution. Well, the revolution rate for 60 cycles is now reduced to 30 revolutions per second, or 1,800 revolutions per minute. So if we double the number of poles, we can cut speed in half without changing frequency. I'll repeat that. If we double the number of poles, we can cut speed in half without changing the frequency. More pairs of poles could be added to further decrease the rotor revolution rate, and this rate would always be equal to twice the frequency in cycles per second divided by the number of poles, all multiplied by the number of seconds in a minute, or 60. For a given number of poles, any change in generator speed will give an equivalent change in the generated frequency. Alternating current frequency is a measure of the number of complete voltage cycles in returns to zero, to an opposite or negative peak, then up to zero again, 60 times every second. Many electrical devices depend on accurate frequency control for their own accuracy and the standard electric clock item. If frequency slows down, so does the clock. Throughout the world, there's a variety of frequencies in use, including zero cycle or DC, direct current. Since so many devices are designed for use with only one specific frequency, it became important in the early days of the electric industry to agree on one common frequency for a given geographic area. In the United States, 60 cycles per second was adopted as standard. In much of Europe and Great Britain, 50 cycle power is standard. You may occasionally come across a 25 cycle generator. These were more common earlier in this century in areas where direct current was used to power streetcars, subways, or large DC motors and equipment. Where large water wheels were used to turn generators, the slower rotational rates produced often made lower frequencies, such as 25 cycles, more practical, and converting lower frequencies to direct current had distinct advantages. One device for obtaining different frequencies is the frequency changer. Two units coupled so they rotate at the same speed. One acts as a motor, turning electrical power into mechanical power or rotary motion. The rotating energy in turn is changed by a generator into electrical power of a different frequency, direct current. This type of system is often called a motor generator set or an MG set. If one generator has 10 poles and generates a frequency of 25 cycles, our formula says it must rotate at 300 RPM. That's 2 times 25, which is 50, divided by 10, which is 5 times 60 to give us 300 RPM. If the other unit is to be a 60-cycle device, it would require 24 poles to operate at 300 RPM. When electric power is supplied, the 60-cycle unit acts as a 300 RPM motor, driving the 10-pole generator, which produces a 25-cycle voltage. In other words, a generator can become a motor, but for best efficiency, a true motor is used to convert electrical power into mechanical energy. Just remember, a frequency changer. Well, at this point, let's review for a moment. A practical generator consists of a stator containing a coil circuit and a magnetized rotor which provides a moving magnetic field. This generator produces an alternating voltage at a specific frequency. The frequency of this alternating voltage is dependent upon rotor speed and upon the number of poles in the rotor. Okay, before going further in this unit, answer the first 6 questions on page 2 of your Trimedia book. Restart the machine for the answers when you've completed the first 6 questions. Okay, let's check your answers. Number 1 is true. A power plant does convert one type of energy to another, to electrical energy. Second question, true. Highest voltage occurs when the force field is closest to the coil. It is weakest when the field is furthest away. Number 3 is also true. If the coil is properly oriented on the stator, the voltages produced will add to or reinforce each other. Hertz is now the worldwide accepted term for frequency in cycles per second. Most of the electricity generated in the United States is 60-cycle, not 50, and most electrical equipment requires 60-cycle power to operate properly, so number 5 is false. 6 is also false. A 2-pole motor, or rotor, shown here, generates only 1 complete cycle as it makes 1 revolution. Okay, if you're ready, we'll continue with alternating current generator principles. And let's go now into the difference between single-phase and three-phase electricity. An AC generator produces a symmetrical voltage curve called wave. The volt grows to maximum, then to minimum, and repeats the cycle. Every change is even and smooth. But the actual power output comes in pulses, much like a single-cylinder gasoline engine. For small power demands, this is quite satisfactory, but for larger power outputs, the gasoline engine designers solved their problems by adding cylinders. These cylinders are arranged so that power is delivered at even the 3 power pulses is much smoother than with just 1 cylinder. Also, with 3 cylinders producing power, there's 3 times more available power, yet the engine is not 3 times larger. The single-coil, single-phase generator, like the 1-cylinder engine, is not very practical for producing large amounts of power. Both produce power in spurts or pulses. Obviously, smoother power output is desirable. So let's solve this problem electrically instead of with cylinders. We'll assemble 3 single-phase generators on a common drive shaft. These units will be labeled A, B, and C, and notice that on each poles are in the same position, but coils B and C have been moved so that the 3 are equally spaced around the circle. Since B coil is located 120 degrees past A coil in the direction of rotor travel, its voltage pattern or sine wave will be 120 degrees later than the voltage pattern from coil A. But since the generators are the same and rotation rates are equal, the sine wave of each will be identical. Our third phase, C generator, begins its sine wave rise 240 degrees after that of coil A. If the sine waves were shown on the same graph, they would appear as shown here. 3 sine waves, each 120 degrees out of phase with respect to each other. Well, this method produces 3 times more power than the single-phase unit, and like the gasoline engine, the sum of their power pulses is, of course, much smoother. But the generator is not 3 times larger. This problem can be solved. 3 stators and rotors are not really necessary. Well, you might ask, why not wind all 3 phase coils on the same stator? Now, the unit is no larger than the single-phase generator, but it provides power from 3 separate circuits. This generator circuit can be represented in a static oracle drawing as shown here. Notice that each coil is independent of the other. Each will be connected with a load, 3 complete electrical circuits. Generator coil ends are labeled for each separate circuit. Notice that small A, B, and C wires all return from the load to the generator together at the generator. This is referred to as a common, neutral, or ground wire. Well, for a brief moment here, let's review electrical fundamentals. In an alternating circuit, voltage or pressure rises to a maximum and again decreases. The sine wave. Well, what happens when the 3 phases are plotted? At any point along the time line, voltages on one side of the zero line will exactly equal the total voltages on the other side. That is, if values are added, the sum of the voltages will always be 0. That is, if the 3-phase generator has a properly balanced load. Now think of voltage as pressure. If the common side of each phase coil is selected, there is no pressure differential between them. The current flow out of one phase will return on the other 2. The voltage in the common return line is 0. As long as the loads remain balanced, there's no current flow in the neutral or common wire. So why not eliminate it? A 3-phase electrical system can carry power from generator to load with only 3 wires. Much more power smoother power than with a single-phase generator, which would require 2 wires anyway. A ground wire using the earth itself often serves as our common, and earth grounds will be discussed in a later lesson. Well, the principles of AC generators that you have just learned won't change. The way engineers apply these principles and the specific equipment used are the subjects of subsequent lessons. Time again for a short exam. When you've answered the questions in Part 2 on your page, restart this film and check the answers. Okay, the answer to number 7 is false. The 3-phase generator may be slightly heavier, but normally is no larger than a single-phase unit. Number 8 is true. The 3-phase generator consists of 3 separate electrical circuits, or phases, spaced evenly around the 360 degrees of each revolution, so they're 120 degrees apart. Pulsing power can be a major problem on electrical systems as well as gasoline engines. Therefore, number 9 is false. Number 10, however, is true. If one phase is at its 0 point, the other 2 must be of equal and opposite values, or the total would not be 0. Question 11 should have been marked true, since a generator converts energy to electrical current, and since a 3-phase generator produces 3 times the electrical output, numbers 12 and 13 are true. 3 wires are normally used to supply balanced 3-phase loads, since no neutral or just a simple earth ground is needed. Finally, number 14 is false. These basic principles of AC generator operation are the same for large or small, single-phase or 3-phase power generators. The principles we have seen developed in this course provide the basis for later understanding of specific operations and design characteristics of various generating equipment you will be working with in your company's power plants. You may repeat this film if you like. Otherwise, you may go on when the machine stops the next time to the next lesson.